So the last term that we haven't talked about yet is the vortex stretching and reorientation term. And this term is arguably the most important mechanism for sustaining turbulence, and especially in the turbulent energy cascade, which we're going to talk about after the Thanksgiving break. So this is an important term in sustaining turbulence. And in the energy cascade process. Basically, how energy moves from large to small scales. So let's write this term out in full so that we can see what it looks like when we talk about the individual components. So the term is vorticity dot the gradient operator times the velocity. And if we look at this, our three different terms have three different directions. In the I direction, we have omega x, the vorticity in the x direction, times du dx, plus omega y times du dy, plus omega in the z direction times du dz. That's all in the I. Plus, next one we'll have omega x times dv dx plus omega y times dv dy plus omega z times dv dz, and that'll act in our j direction. And then the term will also act in the k direction, and this will be omega x dw dx plus omega y dw dy plus omega z dw dz, and they'll act in the k direction. So what we want to focus on is there are these diagonal terms, these three terms here. These three terms represent vortex stretching. The other terms here, the off-diagonal terms, so the other terms are basically the ones that we haven't circled, just our vortex reorientation. So they don't change the vortex, they simply reorient possibly its direction or its rotation as it moves along with the velocity field. Now, one thing we can observe right away we see that for a 2D flow, the vortex stretching term is identically zero. So let's consider a boundary layer flow in the XY plane only. So to understand this or see this, it could be a boundary layer, it could actually be any flow in XY only. Right, so if we have a flow that's a 2D flow basically. The only non-zero vorticity component is omega z in the k direction, right? Right, that's our only non-zero vorticity term as we go through that. However, if we look at this term for the stretching, right here, because this is our only one that's going to be here. Of our stretching terms, only this one has omega z. Well, it depends on the gradient. It's multiplied by the gradient of the velocity field w in the z direction. That's identically 0 for a 2D flow. And in the stretching terms, this is multiplied by dw dz, which is 0 because in our 2D flow, w is 0 everywhere. So we can't have any vortex stretching in a 2D flow, which this is one of the reasons why you basically can't have, and we'll talk about this, it'll come up when we talk about turbulent flow. Turbulent flows are inherently three-dimensional, and this is one reason, is that we have no vortex stretching, so we don't have a mechanism for the energy cascade process to work in the way that we think of it, at least not through breakup of vortexes. We'll talk about that more later. So now let's think about a little bit more what is vortex stretching. So what is this process? So let's consider an example. So let's think about, we have our first kind of example. We have material derivative, the vorticity in the x direction, which this is right, just the omega x du dx plus omega y du dy plus omega z du dz. Now, from a mass conservation standpoint, right, let's think of this, the way we can think of this is let's look at a contraction. It's kind of our interpretation. So we have something that looks like this. And we have basically our initial, say, vortex region, or our initial vortex, and we'll talk more about what a vortex looks like, or a vortex tube, later. That is as vorticity in this direction. It's an omega x at point 1. At point 2, it's going to look something like this. It's going to have much longer. So it's going to be stretched out. Still have omega x here. Note our sense of rotation, we're doing something like this as we go through this. And this would be what we would call amplification of our streamwise vorticity. As we go through this contraction. So from conservation of mass, we know that m dot at 1, m2 are going to have to be equal. And therefore, U2 has to be greater than U1, right? Just from that, it's an incompressible flow. And du dx is greater than 0. So if we assume that we already have an omega x, right? We already have vorticity in the x direction, already exists at 1, then the du dx velocity gradient serves to increase the magnitude at location 2. Right? Kinematically, this basically will result in the stretching of a vortex at location 2 relative to location 1. So in this example, it's a contraction, but this is actually something we can say for any time we have a acceleration, really.